Hi all, thank you for coming to my talk. My name is Brandon Biscano, and I'm a graduate student at Stanford University in Joseph Kahn's Optical Communication Group. And today I'll be talking about coherent co-packaged optical interfaces used for next-generation data center electrical switching. So let's get into it. First off, here are some data center trends on the right. And you can see that there is a significant amount of traffic. In fact, 77% of IP traffic is projected to reside within the data center. And this data center IP traffic is growing at a compound annual growth rate of 27% over 2015 to 2020. So there's a huge demand for bandwidth within the data center. However, increasing this bandwidth is problematic. For example, the front panel of the data center racks for switches is severely space limited. Additionally, the power consumption is scaling exponentially. The complexity of the data center design is also scaling really poorly because the amount of single mode fibers needed to connect different racks is also significantly increasing. Also, in order to meet the demands of the link budget for the next generation of links, the optical power has been increased, but this has led to some issues with eye safety. And finally, in order to enable flexible technologies like optical switching, there are some issues that need to be addressed. So over the past few years, several large organizations have proposed the use of co-packaged optics and to alleviate a lot of these issues. So what is co-packaged optics? Well, simply, it's moving the optics closer to the electronics. So here you have your typical pluggable optics here, where you then route your electrical signals all the way to your switch chip. Now, as you can move them closer, so you move your optics closer to the switching ASIC. And finally, you can put it on the same package, within the same package as the ASIC. And in doing so, you eliminate the necessary electrical connections, the long electrical connections that tend to be lossy and require retiming, so you reduce power consumption. And then also, your front panel is composed of fiber connections rather than bulky transceivers. So these are just a few of the ways that co-packaged optics can improve future data center switching. Well, let's talk a little bit more about what that means, and in particular about the challenges associated with them. So temperature fluctuations are a significant issue because due to the bursting nature of the switch traffic, there are large temperature fluctuations next to the chip. However, putting active optical elements closer and closer to this switch means they're exposed to this temperature-sensitive environment, which is traditionally not very good for two main components, the laser and the multiplexer and demultiplexer for wavelength division multiplex systems. We'll talk a little bit more about this later. Second, the on-chip insertion loss is much higher for integrated technologies. So, for example, current fiber-to-chip technology increases insertion loss, as well as in integrated waveguides, modulators, photodetectors. The optical loss associated with these components is much higher for integrated technologies. So you might say introduce optical amplifiers for this, but this will increase amplifier noise, ASE noise, and it will also increase the overall cost of the system. And finally, what you might say is, well, let's just use higher power lasers. Well, fibers that can be accessed by technicians inside the data center need to be safe. And so in this case, you need to make sure that when you add high power lasers, you're doing it in a safe way. So these are just a few of the challenges associated with integrating intra-data center links. So here is a proposed ISafe temperature insensitive architecture for co-packaged optics. So I'll just walk you through what's exactly happening here. So here we propose using an external optical source. So the laser is located away from the switch chip, and it's a multi-wavelength source for WDM communications. Then this external optical source is coupled onto the photonic integrated circuit here, where it's demultiplexed and sent to bank of modulators here, and then remultiplexed and sent to the ISafe signal path. Now, you'll notice that I've labeled these as dual polarization IQ modulators, which are coherent modulators, but you could also use this with direct detection modulators, and we'll talk about later about the comparison between direct detection and coherent detection. So once it reaches the ISafe signal path, it may or may not be amplified, and then it gets coupled onto the receiver PIC, which is located at a separate switching ASIC, close to one, and where it is demultiplexed and sent to a receiver. Now, if you're using coherent technology, you need a local oscillator. So another optical multi-wavelength source will then be coupled onto the chip and used as demultiplexed and used as a local oscillator. Now, I mentioned before that there are two main components that are heavily affected by the temperature sensitivity of the chip. One is the laser, which we've now located off the chip, but the second one is the multiplexers. And what happens to the multiplexers is their passband will shift when exposed to temperature in a bursty temperature environment. So let's talk a little bit more about how we can reduce the effects of the thermal environment on multiplexing. So here, the idea is to use coarse AWGs, which have a larger passband, to demultiplex the input signal. Then you use coherent detection with electrical filtering to eliminate the crosstalk. I'll walk you through how this would be done in one case. So say you have 8 wavelengths incoming. Instead of immediately putting them into a multiplexer, what you do is you have a small amount of power splitting, usually like in this case a 1x2 power splitter, that takes all the channels and then passes them through a wide band AWG, which is a demultiplexer. So when you look at one of the coherent receivers, so you're trying to target channel 1, for example, in this coherent receiver, what you see is that you actually have artifacts of channel 2 inside your signal. However, because you're using a local oscillator here, and after it's combined on the optical hybrid and through balanced photodetectors, you can electrically filter the second channel away. And so in doing so, you've allowed for temperature fluctuations so that the broadband AWG can shift, but you also can avoid, so you can avoid that effect. However, what you do have is you have an additional power splitter, which will give you an optical insertion loss penalty. And we'll discuss what this looks like in the next few sections. So before that, let's talk about exactly how you model these types of systems. So here's a coherent detection right here, and you can see that you have your input INQ signal, and this is the modulator, and this is the receiver with the 90-degree hybrid, balanced photodetectors, transimpedance amplifiers, and low-pass filtering in order to remove these other neighboring channels. So when we consider these, we consider ASE, shot noise, and thermal noise, which in this case, because we're measuring the electric field of the input signal, they can all be assumed to be Gaussian. However, in the direct detection case, when you just have a single direct detection modulator on a photodiode with some transimpedance amplifier and filtering afterwards, in the presence of ASE and thermal noise, shot noise is not relevant for these systems, you see that there's in fact non-Gaussian effects, and this is due to the beating between the ASE noise and your signal at the photodetector. So you need to do a little bit more of a detailed analysis of the noise statistics. And this is the probability density function of the received levels in the presence of extreme ASE and thermal noise. So additionally, we also consider non-ideal modulation. So with limited drive voltage, finite extinction ratio, and electronic crosstalk. So we model these impairments and put them into our modeling simulation. And then these are additional parameters that are associated with our link. So we have the transmitter parameters. So in this case, we're assuming something like 56 gigabaud. The signal path, where we have some eye safety limit, and then a receiver that's associated with the local oscillator. So let's look at how these systems perform. Okay, so traditionally, loss budget is a valuable metric for the data center. So here, well, first I'll start here. You can see here are 4 different plots of the loss budget for different types of demultiplexer passband shifts. So here, this is plus or minus 0 gigahertz. What this means is that the multiplexer passband is not moving at all. So this is a case where the temperature is essentially fixed. And what you can see is just generally, these curves tend to outperform the other curves in terms of loss budget as you scale towards higher systems. Now this makes sense because and you would expect that in the presence of temperature fluctuations that your performance would decrease. So so here this is 0 gigahertz and this is 50 gigahertz, 100 and 150 gigahertz associated with a significant amount of temperature fluctuations. So your shifting of the passband is associated with, say, in this case, a significant shift, which would be 150 gigahertz. So in this case, we compare 3 different architectures and 4 different modulation formats. So I'll walk you through them here. The blue and red curves are associated with direct detection modulation formats. So this is non-return to 0 on-off keying and 4-PAM, which are traditionally used inside the data center today. Here we have coherent technology. We have coherent modulation formats, so dual polarization QPSK and dual polarization 16QAM. And finally, we have systems that are completely unamplified with the triangles. The squares are booster amplifier only, and then a second level of amplification associated with booster and preamplifier here. And unsurprisingly, the performance of amplified system outperforms on unamplified systems. But you'll notice something really stark, which is that the direct detection modulation formats in terms of bitrate per fiber do not scale as well in terms of loss budget as their coherent counterparts, even in the presence of optical amplification. So while the next few generations, which are associated with, say, 400 gigabits per second all the way to 1.6 terabit per second, may be able to tolerate using direct detection, future high bitrate per fiber technologies will necessarily need to use coherent detection and wavelength division multiplexing. So here's the loss budget. So this is the loss budget. And through these plots, you can analyze and you can see what type of noise regime you're in. So, okay, so for the amplified systems, you have your ASE noise dominating for low bit rate per fiber systems. And when you really start to press your bit rate per fiber up towards 10 or more terabits per second, you see thermal noise dominating because of the ISafe limit. And finally, you can see these jagged drops in the coherent output. And this is related to what I mentioned earlier about the power splitter ratio increasing in the athermal receiver. So as you need to, as the temperature sensitivity increases, you need to split your power more to different channels in order to ensure that you can tolerate the passband shifts. So you can do a similar thing for the OSNR, and similar to loss budget of amplified systems, you can see here. And you also see this jagged, these jagged effects associated with the power splitter for the coherent technologies, though they do scale to higher bit rates per fiber. The additional transmitter loss, there is additional transmitter loss associated from the athermal design, which reduces your OSNR. So eventually, I'd like to talk a little bit more about our external light sources for co-packaged optics. So this is some ongoing work in our research group, and it's widely believed that external light sources are the solution to enable co-packaged optics. So the reasons for this are relatively straightforward. They're more reliable, so integrated lasers might actually fail on the chip and you have no way to replace them. Serviceability, the complexity associated with on-silicon lasers are difficult and costly to make. They usually increase the footprint. So for example, integrating many lasers onto this PIC will actually allow for fewer transceiver components to be placed on the PIC as well. Temperature, the integrated lasers may suffer penalties due to the bursty temperature environment. However, there are still problems associated with these external lasers. For example, the insertion loss associated with coupling and routing the optics onto the silicon introduces additional link budget penalties. The power consumption of high power lasers, they're just less efficient at higher powers. The complexity associated with fiber attachment and management is an extremely important issue and will limit the total switch bandwidth. You have high power penalties associated with nonlinear loss in silicon in particular, or you can have some damage with certain epoxies, optical damage. And finally, eye safety of high power external lasers, it might be dangerous to untrained technicians. So even though it's not obvious how to best design the external sources to account for scalability, they need to double, the switch bandwidth needs to double every 2 years. So in this presentation, I hope you got a good understanding of how we can look at co-packaged optical interfaces and understand how they perform in next generation data center switching environments. So thank you for coming to my talk.